if you so wish, for whatever reason. All right, let's see. Here we go. IPC class. So we are in week 4 of this class. So we are almost halfway through the end of the term. A couple announcements that I wanted to make before we get started here. The first one is that Monday, May 3rd, so next Monday, is a holiday for daytime students. So that includes this class. We are a day school class. And so there's going to be no attendance, no daily assignment, nothing to check in and do on Monday for this IPC class. We'll still come back together like this on Tuesday next week, just like normal. But Monday next week will be a holiday for y'all. Other thing that I want to mention is that since we are here at the halfway point in the term, that means that our midterm exam is coming up. So the midterm is essentially like a big assignment for you guys to work on. I'll talk about it a little bit more in detail at the end of class today, just to kind of get you guys prepped for it. But essentially, it'll be posted on Wednesday, which is tomorrow, but it's not due until Friday. So you have all day, Wednesday, Thursday, and Friday to work on it and get it turned in. And like I said, it's a little bit bigger, it's a little bit longer than most of the homework assignments that we have in this class. And there's questions on it that cover a whole range of all the topics that we've talked about so far. So from the solids, liquids, and gases, the phase changes, the heating curve, the atoms and the protons, neutrons, electrons, all sorts of questions about that stuff will be on the midterm. The handy thing is that the midterm is open note. So you will have access to all of the notes that are posted on the Google Classroom here while you're working on the midterm. Again, I'll go into it a little bit more at the end of class today, kind of show you how it's set up. But I just wanted to bring it up here at the beginning, just so that you are aware of it. So again, it'll be available to start working on Wednesday, but it is not due until Friday. So you have, starting Wednesday, you have the entire rest of the week to work on it. All right, including, I will say, some of the stuff that we cover this week in these notes could also be on the midterm as well. So it covers everything from the first 4 weeks of class, including this week we're in right now. All right, so today we're going to talk about how atoms get joined together, how they get bonded together through a process called chemical bonding. So when we talk about atomic bonds, no, we are not talking about this bond. And no, we are not talking about this other better bond. We are talking about chemical bonds, or the bonds that atoms make with each other in order to join together and build larger structures, larger objects, larger pieces of matter. So we've been talking a whole lot about atoms from the past couple weeks. So here's a pretty basic atom. Here is a helium atom. So an atom has 3 different parts to it, right? There are these 2 different types of particles here in the middle, and this one type of particle here on the outside. So let me give you guys a super quick little quiz right here. What are these positively charged particles in the center part of the atom? What are these guys called? Protons, exactly, Alexia. Good answer. So protons are positively charged, and they hang out here in the what's called the nucleus of the atom, the center area of the atom. What about these gray particles here? They're also here in the center of the atom, but they don't have a charge. They're not negative. They're just kind of hanging out here in the middle.
Neutrons.
Bingo, exactly. So neutrons are neutral. They don't have a charge. Protons are positive. They have a positive charge. And both of them hang out in the middle here in the what's called the nucleus. What about these little negative guys on the outside? What are these guys?
Electrons.
Electrons, exactly. These are the guys that we spent all day on Thursday talking about, are electrons. So electrons don't go in the middle of the atom. They instead go on the outside, and they occupy those shells like we were talking about, right? So in the case of helium, helium has 2 protons, 2 neutrons, and 2 electrons. So helium only has that first electron shell on the outside right here, and it's nice and full with 2 electrons. Remember, 2 is the maximum that can go on our shell number 1 right here. So the way that you figure out how many electrons an atom has is that you can look at its atomic number, right? Each atom has an atomic number, and the atomic number tells you how many protons and how many electrons are in an atom. So helium, for example, has an atomic number of 2, which means helium has 2 electrons and 2 protons. So our electrons, they differ in their energy levels, and based on their energy levels, they go on different electron shells. So 2 electrons go on that first shell, then the second shell can fit a total of 8 electrons, and the third shell, if we need it, can also fit a maximum of 8 electrons. That was something that tripped a lot of people up on the homework question yesterday. A lot of people said that there were 18 electrons on the third shell. That is not
Which 8?
Of the electrons we're looking at in this class. If you Google it, some sites will tell you that 18 electrons are on the third shell. They're talking about a little bit different third shell than we are. That's getting into a little bit more advanced concept of like different configurations on the different shells. And we're not worried about it in this class. So as far as this class, as far as IPC is concerned, the third electron shell can fit 8 electrons. Not 18, 8. So one of the things that we did not talk about on Thursday is that these electron shells determine how an atom interacts with the other atoms that are around it. Especially whatever its most outside shell is, that will determine what kind of interactions that the atom has with other atoms. So today we're going to focus a whole lot on electrons that are on the outermost shell of an atom. Again, first electron shell can fit 2 electrons, and each shell thereafter, the second shell and the third shell, can hold up to 8 electrons. That is the rule that we are working with in this class. 8 maximum on shell number 2 and shell number 3. So because these outermost electrons are so important, whether they're on the second shell or the third shell, which other ones are on the most outside shell, they're so important that they get their own special name. We call them valence electrons. So valence electrons are the electrons that are on the outermost electron shell. So if our atom only has 2 electron shells, then the valence electrons are the ones on the second shell. If the atom has 3 electron shells, the valence electrons are the ones on the third shell. So we have these electrons. They're on these shells, and they're added there based on these rules of 2 and then 8 and then 8. And our valence electrons are the most important ones. So here are a couple simple kind of drawings, illustrations of some different atoms. We can look at a super simple atom like hydrogen. Hydrogen only has 1 electron. And so hydrogen has 1 valence electron, because that's the only one that's out there, right? It could fit 2 on that first shell, but it only has 1. So that's what these little white dots indicate, the little white circles. They indicate electrons that could go on that shell, but aren't filled in because we ran out of electrons. So for a little bit better example of that, let's look at carbon. Carbon has an atomic number of 6, which means that carbon has 6 electrons. So in order to figure out the shells, we put the first ones on the first shell, 1, 2. Then on our second shell, we put the remaining leftovers, which is 4. So 1, 2, 3, 4 electrons on the second shell of carbon. So carbon has 4 valence electrons, right? Its second shell is the most outside shell of carbon. And on that second shell, carbon has 4 electrons. So carbon's got 4 valence electrons out here. If we move up 1 to nitrogen, nitrogen has an atomic number of 7. So it has 7 electrons, 2 on the first shell, and 5 on the second shell. So nitrogen has 1 more electron than carbon. So nitrogen has 5 valence electrons. 5 electrons on this second shell right here. 1, 2, 3, 4, 5. Oxygen, like what you guys were looking at for that homework assignment from the other week. Oxygen has 2 electrons on the first shell out of 8, and then the remaining 6 go on the second shell. So oxygen has 6 valence shell electrons. 6 valence electrons here on the outsidemost shell of oxygen, which is shell number 2. So valence electrons, the ones on this outside shell, and how many valence electrons you have depends on how many total electrons you have and how many that get filled up on that outside shell. So one really, really important reason why we like to keep track of these valence electrons is due to something that scientists discovered that they named the Octet Rule. So octet is sort of like 8. So, you know, like an octagon has 8 sides and octopus has 8 legs. So the Octet Rule says that atoms want to do whatever they can so they can have 8 electrons on their outer shell. So some atoms will gain more electrons, some atoms will lose electrons, or some atoms will share electrons with other atoms so that they can get up to 8 electrons. They really, really want this outer shell to be full. That's what the Octet Rule says. We're trying to make it so that they have 8 electrons. So carbon, like we were just looking at earlier, carbon has 1, 2, 3, 4 valence electrons out of a possible 8. So carbon wants to gain 4 more electrons, right? In order to have a full second shell, carbon would need 4 more electrons in there in order to make this full. So carbon has 4 electrons already. It wants to gain 4 more in order to get up to 8, so it can have a nice full outer shell. Nitrogen has 1, 2, 3, 4, 5 valence electrons, and 1, 2, 3 spots available. So nitrogen wants to gain 3 electrons, right? It already has 5 out of 8 on the second shell. So if it could get 3 more electrons in there, if it could do something with other atoms to get 3 more electrons, then it could get up to that magical 8 number. Fill in that octet rule and get up to 8 electrons. So nitrogen has 5 valence electrons. It wants 3 more to get up to 8. Similarly, oxygen has 1 more electron on there. So oxygen naturally has 6 electrons in its valence shell. So oxygen wants 2 more electrons in order to get up to 8. So carbon has 4 valence electrons, so it wants 4 more. Nitrogen has 5 valence electrons, so it wants 3 more. Oxygen has 6 valence electrons, so it wants 2 more. Again, it's all about trying to get that 8 electrons on the outer shell. So whatever atoms have to do in order to take or lose or borrow or share in order to get up to that 8 electrons, that is what they are trying to accomplish. That is what they will naturally do when they encounter other atoms, is try to rearrange their electrons so they can get up to 8 on that outer shell. All right, so I know this is a whole bunch more electron information that I'm throwing at you guys here. Does anybody have any questions so far on valence electrons, the octet rule, anything that I've gone over that you're still a little confused about? All right. Doesn't sound like anybody has any pressing questions at the moment. So good. Sounds like everybody so far kind of understands this okay. So again, valence electrons are the ones that are on the outside shell, and all atoms want to try and make it so that they have 8 electrons on that outside shell. Here are some more examples of atoms and their electron setup. So here's the 3 that we were talking about earlier. Carbon has 4 valence, nitrogen has 5 valence, oxygen has 6 valence. One of the cool things about the periodic table and the way that it is set up is that in general, as you go up and down a column, which is called a group or a family on the periodic table, you might have different electron numbers in total, but the atoms will have the same number of valence electrons. Like, for example, carbon has 4 valence electrons on the second shell. Silicon has 4 valence electrons, but they are on the third shell. So carbon had 6 electrons, so it has 2 on the first and 4 on the second. Silicon has 14 total electrons, so it has 2 on the first, 8 on the second shell, so it has a completely full second shell, but 4 on the third shell. So carbon and silicon both have 4 valence electrons. It's just carbon's outer electrons are on the second shell, and silicon's outer electrons are on the third shell. Same thing with nitrogen and phosphorus. Nitrogen has 5 valence electrons on the second shell. Phosphorus has 5 valence electrons on the third shell. Oxygen, like we were just talking about, 6 valence electrons on the second shell, and then sulfur, 6 on the third shell. So again, the valence electrons, the ones that we are most concerned about, are the ones that are on the outsidemost shell. So we don't really care about the 2 electrons on oxygen's first shell, and we don't really care about the 10 electrons that go on sulfur's first and second shell. Those guys are kind of there, they're staying put. We only care about the outside electrons. So some atoms have an extremely full outer shell, like neon and argon over here. They both have 8 electrons on their outer shell. Neon has 8 second shell electrons, and argon has 8 third shell electrons. So neon and argon, you may remember it from Thursday, I mentioned that they belong to that group of noble gases, so they already have a full shell. They don't need to satisfy the octet rule because they already have 8 electrons on their outer shell. So these guys don't really react, they don't really do any sort of electron moving with any of the other atoms. They don't need to. They're already at a full outer shell. So these guys are happy just doing their own thing and not interacting, not mixing, not combining with these other atoms over here. Some atoms are really close to having a full shell, like fluorine over here has 7 outer shell electrons, so it just needs to gain or share 1 more electron to get up to 8. Some atoms, like sodium over here, they've only got the 1 valence electron. So 2 and then 8 makes 10, but sodium has 11 electrons, so that last one goes on the third shell here. So in order to make to that octet rule, sodium would have a really hard time gathering up 7 more electrons in order to fill that shell. But the other thing atoms can do is they can give away their electrons. So sodium could lose this electron right here, and then it would have a nice full second shell, and that would become its outside shell. So depending on what kind of atom that you're dealing with, some atoms are more inclined to lose their electrons. Some atoms are more inclined to take electrons from others, and some atoms have a tendency to more often share their electrons. And so we're going to talk a lot about that in kind of the second part of the notes today, is how it is that atoms either give and take or share their electrons in order to get to that full outside shell. Sometimes you'll see valence electrons drawn like this. So they're called electron dot structures. And since the valence electrons are the only ones we really care about, we don't always want to have to go in and draw all of the shells with all the inside electrons on there. And so instead, scientists came up with a way to just write down the symbol of the atom and then only fill in the valence electrons as like dots around them. So like carbon, remember, has 4 valence electrons. So we have 1, 2, 3, 4 dots around our C. Nitrogen has 5 valence electrons, 1, 2, 3, 4, 5 dots around nitrogen. Oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6 dots around the oxygen, and so on and so forth. You won't see these all the time, like I don't think I really use them on the homework, but I wanted to bring them up in case you see them either later in the notes or in the future. You won't be confused about what all these dots around them mean. It's just an easy way to show what the valence shell electrons of an atom look like. So again, notice carbon and silicon in the same family, and so they each have the same number of valence electrons. 4 for carbon, 4 for silicon. Same with nitrogen and phosphorus, they both have 5, and oxygen and sulfur both have 6. So the main way that atoms come together, join together in order to create a new structure, a new compound, is called a chemical bond. So atoms will chemically bond to one another as an attempt to fill in their electron shells. So the reason why atoms are bonding and coming together and joining together is so that they can share electrons or give and take electrons in order to get to that outer 8 shell. And so when they do that, it causes them essentially to become stuck together. And when they do that, they go through a chemical change and become a new substance. So remember way back on the first week of school, we talked about physical and chemical changes. And I mentioned that chemical changes are when you start off with one set of substances, but then they change into new chemicals, new substances. Well, the way that they change is that they make different chemical bonds. So the atoms that were there in our original substances, they get moved around, they bond to different atoms in a different way, and that creates a new substance. So there are 3 different types of chemical bonds, but really only 2 major ones that we're going to focus on today. So today we're really going to look at ionic bonds and covalent bonds. Metallic bonds we'll talk about briefly, but they're not really important for the stuff that we're going over. But ionic bonds and covalent bonds, these guys are what we're really focusing on. So the main way that they're different is that in ionic bonds, we transfer electrons from one to another. So that's where you have a give and a take of electrons. And covalent bonds, we share the electrons. So covalent, like multiple valence electrons. So instead of giving and taking, instead, both atoms share. And so today we're going to look at exactly how ionic bonds and covalent bonds form and what they look like when they do. All right, so ionic bonds. These guys are all about transferring the electrons, moving one or more electrons from one atom to another atom. So ionic bonds is where you have the give and the take. One atom is giving away its electrons, and the other atom is taking the electrons. So ionic bonds tend to happen between metals and nonmetals. Remember, metals make up most of like the left and middle section of the periodic table, and nonmetals tend to be over on the right-hand side. And it's all about transferring electrons. So they're not sharing, they're giving and taking. Don't really have to worry about that third point there. Main thing to remember is this transfer of electrons. So common examples are things like sodium chloride. Remember, sodium is a metal and chlorine is a nonmetal. Calcium chloride, again, calcium is a metal, chlorine is a nonmetal. Potassium oxide here, so K is potassium and O is oxygen. So potassium oxide, because potassium is a metal and oxygen is a non-metal. So these guys are all formed due to ionic bonds. And so the way that ionic bonds actually work, the way that they look like, and I apologize, I don't have any way to like pause or stop this animation, so it's just gonna kind of keep running while I'm talking. But over here we have sodium in the gray, and remember sodium has 1 valence electron. So that's the little yellow dot that's moving around here. That's sodium's valence electron. Chlorine over here in the green has 7 valence shell electrons. So that's what the red dots around chlorine represent. 7 electrons on chlorine, 1 on sodium. So sodium really wants to give away that electron so that it can have a second ring that's full of 8 electrons. So right now it's got a third ring that has the 1 lone electron on it. If it can get that away, then its outside ring will become the second ring, or the second shell, and that shell already has 8 electrons. So sodium is trying to give away this one little lonely guy hanging out here. Chlorine has 7 valence electrons, so it really wants one more electron in order to get a full set of 8 around the third shell there. So when these guys interact with each other, sodium's like, hey, I'm really trying to give away this last electron. And chlorine's like, hey, I really need one more electron. So the electron transfers. It moves from sodium over to chlorine. Now sodium is happy because he gave away that lone electron, and now he has a full set of 8 on the second shell. And chlorine is happy he took that electron. So now chlorine has a full set of 8 on its third shell. So this is how an ionic bond actually forms. One electron, or one atom, gives away some of its electrons. Another atom takes some of those electrons. So that's nice. Now they're both happy. They both have 8 valence electrons. But we're making a bond, right? They're sticking together. They're not just going to float off and do their own thing after this. They're going to become a new compound, sodium chloride. And so the reason why that happens, again, it's kind of like, I found these little diagrams online. It's like one atom is the big dog that takes the bone, and the other atom is the smaller bond that loses the bone to the big atom. So the reason why exactly they get stuck together is because when sodium gives away its electrons, it becomes a little bit more positive. Because it started off with 11 protons down here and 11 electrons up here. But now there's more protons than electrons. There's one more proton. So sodium, because it has more positive charges, becomes a little more positive. Chlorine took that electron. It took that negatively charged electron. So now chlorine has an extra electron to what it did before. So chlorine is now a little bit negative. And in science, an important rule in science is called opposites attract. So in science, when you have a positive charge and a negative charge, they're naturally attracted to each other. So this is what causes sodium and chlorine to bond together and become sodium chloride. It is because sodium gives away that negative electron and becomes a little bit positive. Chlorine takes that negative electron, becomes a little bit negative, and then the positive sodium and the negative chlorine naturally are attracted to each other. And that's what makes the bond part of the ionic bond. One atom becomes a little bit more positive, one atom becomes a little bit more negative, the opposites attract, and the atoms become stuck together. They become bonded to each other. So again, ionic bond, all about that transfer, all about giving away that electron. So the sodium electron leaves, sodium becomes a little bit more positive. The chlorine takes that electron, it becomes a little bit more negative, and then the positive and the negative are attracted together. They make that bond of sodium chloride. So you might recognize sodium chloride because you actually probably have a whole bunch of it in your house right now, because sodium chloride is salt, like typical normal table salt is sodium chloride. Sodium and chlorine atoms, usually tons and tons of them, that have all become stuck together as part of these big ionic bonds. So the sodium and the chloride are bonded to each other thanks to moving that electron, transferring that electron from one to the other. So ionic bonds, all about moving the electron from place to place. You get a little bit more negative, you get a little bit more positive, and then those guys become bonded together in order to make the atoms stuck together, turn them into a new compound, go through that chemical change. So this is a chemical change that we have going on right here, right? We started off with two different substances, sodium and chlorine on their own. Then when they become bonded together, they make a new substance, sodium chloride. So this guy was not there before. This is a new substance that we formed because of this chemical change, moving the electron from one to the other. All right. Does anybody have any questions on ionic bonds so far? Anything that you're still a little bit confused about or not sure on? All right, seems like everybody's feeling pretty okay with our ionic bonds so far. So then, if that's the case, then we'll move on to our next major type of chemical bond, covalent bonds. Bonds that are formed by two atoms sharing their electrons. So we're not giving and taking anymore. Instead, we're sharing the electrons between the atoms. So this tends to happen between nonmetals. So over on the right-hand side, if you have two or more of those coming together, that's what tends to make covalent bonds. And it's all about sharing pairs of electrons. So like carbon dioxide, right? The stuff that we breathe out when you exhale. Carbon and oxygen are both nonmetals. And so if you get two oxygens, they can covalently bond to one carbon. Same thing with H2O over here, the world famous water molecule. Water is also made out of two covalent bonds. One oxygen is bonded to two hydrogen atoms. So again, we're not giving and taking the electrons. Instead, we are sharing them. So for an example of what this looks like, let's consider a very simple molecule called CH4. One carbon and four hydrogen molecules bonded together. If you remember, carbon has four valence electrons. So the carbon electrons are here in blue. 1, 2, 3, 4. These are our valent carbon electrons. Hydrogen has only that one valence shell electron, and so hydrogen is trying to get up to 2 electrons, right? Because hydrogen is one of the weird ones where it only has the one shell, so it doesn't exactly follow the octet rule. It's not trying to get to 8, it's just trying to get to 2. So carbon has 4 valence electrons. Hydrogen has 1. So when they first meet up, carbon's like, hey, I have this one electron. You have this one electron. Let's share them together to make a pair of electrons. So each one of these guys brings an electron into the pair and they share it. So now this hydrogen feels like he has 2 electrons right here. And this carbon feels like he has 2 electrons right here. They're sharing these electrons together. Same thing with up here. Carbon's like, hey, second hydrogen, I have another electron that's not paired up with anybody. And the hydrogen's like, okay, I can pair up with that. So they share their electrons with each other. Now this hydrogen feels like he has 2 electrons, and the carbon feels like it has 2 electrons here as well. Same thing happens over here and over here. Carbon shares one of its electrons with hydrogen, and hydrogen shares one of its electrons with carbon. So now each one of these hydrogens is happy because they feel like they have 2 electrons on the outer shell, their own electron and then one that they're sharing with carbon. So we have 1, 2, 3, 4 hydrogens that all feel like they have 2 outer shell electrons. And this carbon is happy because he feels like he's got 8 outer shell electrons. He's got his 4 that he started with, and 1 more that each one of the 4 hydrogens is sharing. So again, it's all about sharing these pairs of electrons. 1 from carbon and 1 from hydrogen in each one of these groups. And so this is normally how like covalent electrons are written. They're kind of shown by these 2 atoms that have these overlapping electron shells that each have multiple electrons on them. Again, covalent, they're sharing their valence electrons. So this valence electron originally belonged just to hydrogen, but now because they're sharing, it belongs to both hydrogen and carbon. So it's covalent. It's valent for 2 different atoms. And that's what our covalent bonds are all about, sharing these outer shell electrons. Same thing with this little diagram right here. So in this case, we have 2 atoms that each has 7 electrons on its valence shell. So maybe this is something like fluorine or like chlorine that we were looking at earlier. Chlorine has 7 valence shell electrons. And so in this case, unlike with sodium, where chlorine took the electron from the other atom, in this case, when 2 chlorines meet up together, they both share their 7th electron with each other. And so it makes both of them feel like they have 8 valence electrons. So this guy feels like he has 7 on his own, plus the 1 that he's sharing with the other one. Same thing with this guy. He feels like he has 7 of his own electrons, plus 1 that he's sharing with the first chlorine. So coming together, and they become joined up, they become bonded together because now they are physically stuck together. They're both sharing that 1 or 2 electrons on their outer shells. So their outer shells become stuck together, essentially. And that's what causes that bond to form. So covalent bonds are all about sharing these electrons, each atom making use of the multiple electrons. So this one is a little bit more simple than ionic bonds. We don't have the give and take. We don't have the positive and negative thing that's going on. It's just multiple atoms that come together and share their outer shell electrons in order so that both atoms can feel like they have that full valence shell. All right, does anybody have any questions about covalent bonds? Anything that you're still confused about with these covalent bonds here? All right. So the last one I'm just going to go through really quick because we're not really going to focus on it too much in this class. Metallic bonds are another type of bond. that tends to form between metals. Like when you have a bunch of metal all together, it'll make metallic bonds. These are what make metals good conductors. So remember, metals are really good at conducting heat and electricity, moving those around. That has to do with these metallic bonds. And essentially, it's like the electrons from the metals can all just kind of mix and match with each other. They're not giving and taking necessarily. They're not bonding them together. They're all just creating this like sea of electrons. All these electrons that can just kind of move freely across all of the metal atoms. But like I said, those ones you don't have to worry about so much. We're not really going to focus on that in this class. It's the ionic bonds and covalent bonds that are the big ones. These are kind of the most important ones to know, especially for IPC here in term 5. So, fittingly enough, your assignment for today and tomorrow are all about these valence electrons and these different types of bonds. So the one from today, pretty easy and straightforward. There are a couple diagrams. So we have this diagram right here of lithium and fluorine making a bond. And we have this diagram right here of hydrogen and fluorine making a bond. And all I want you guys to do is tell me what kind of bond is in the diagram that is shown, and how can you tell? What is it about this diagram that tells you it is a covalent or an ionic bond? So just a quick, short little, like 5 to 10 word answer, 1 sentence answer about what makes one of these a ionic bond and what makes one of these a covalent bond. So pretty straightforward one for today. And then tomorrow, I think, is just a daily question about the Octet Rule and valence electrons. So essentially, what is the Octet Rule and what does it have to do with valence electrons? So again, if you need a little bit of a refresher when you get to tomorrow and these words sound kind of familiar, but you can't remember exactly what they mean, you can always go back and look at the chemical bonding notes that we just went over today, because they are posted now and forever right here. Today is 4/27. And so if you ever want to go back and look at these chemical bonding notes again, you can find them right in this little section of the Google Classroom right here. All right, any other questions about valence electrons, Octet Rule, ionic covalent bonds, or any of the homework assignments for today or tomorrow? All right, cool. Thanks, Rosita. Sounds like most people also don't have any questions. Last thing, I mentioned that I was going to go talk about the midterm again before we left. Again, it'll be posted tomorrow morning, just like a normal daily assignment. But since it's longer, much longer than a daily assignment, you have until Friday, so the end of the day on Friday, April 30th, in order to finish the midterm and get it turned in. Again, you can do it on Google Docs if you want, or you can do it through the Google Forms. The Google Forms is a little bit different than some of the other ones, just because since it's a lot longer, I broke it up into sections. And so you answer the questions in each section before you move on to the next one. So like the first one is just typing in your name and then a little bit of information about answering questions. And then you'll hit next. There's some most of them are multiple choice questions. There's some like fill in the blank questions. There's some short answer questions. There might be some matching questions. And so you go through, answer them all, hit next, go to the next section, and then just keep hitting next until that submit button comes up. I believe that there's 3 or 4 sections that you'll go through. I think it's about 20 to 25 questions or so long. I forget exactly how many there are. But again, you have 3 full days to work on it: Wednesday, Thursday, and Friday. So take your time, read each question carefully. None of them are like trick questions, but it always is a good idea to read and make sure you know what the question is asking before you answer it. Like I said, it is open notes, so you're free to go back and look at any of the notes from the previous weeks that we went over if you think that'll help you answer the question. If you ever get stuck on a question and you're not quite sure what it is asking or how to answer it, please feel free to reach out to me. Obviously, I can't directly help you figure out the answer, but I am more than happy to help you figure out what it's asking or what type of answer that it's looking for. I don't want anybody to miss any questions or get anything wrong just because they didn't understand the question or they didn't understand what type of answer to put down. So if you have issues like that, if you get stuck and you're not really sure what to do, always feel free to reach out to me and I'll do what I can to help. So again, that is our midterm exam for the class, going up tomorrow morning, due by the end of the day on Friday. All right, anybody have any final questions about anything that we talked about so far today? Anything else that you want to know?
No, sir.